Okay, welcome to another Simple Engineering Snippet. In this video, we are going to be showing how we can set up the loop equations to solve for the flow in this hydraulic network. I hope you find it useful. Okay, so what are the loop equations? Well, there are a couple of different ways to set up equations to solve network flows and heads. These are the loop equations where the unknowns are the flows in the pipes. And so the number of unknowns is equal to the number of identified pipes. If we have 7 pipes, as we do in this example, I'm going to need 7 equations. And where do they come from? Well, we're going to apply conservation of energy and continuity. And we are going to be working through this example in detail to show you exactly how to do that. What we are not going to be doing is solving for the actual flows or the heads. And there are various techniques to actually solve the equations that we are going to be setting up. Could be the Hardy-Cross, could be the linear method, the modified linear method. What we're doing in this video is concentrating how to set up the loop equations for applying one of those techniques to obtain a solution. Okay, typically when we solve networks, we choose to work in volumetric flow Q. Typically this would be a incompressible fluid, and we'll be working with a piezometric head. As a reminder, piezometric head is the pressure head plus the elevation. So essentially we'll be calculating the hydraulic grade line around the network. Pipes, what do we mean by pipe? Well, it's a section of constant diameter. So if you have a straight section of pipe that changes from 6 inches to 4-inch diameter, then that's got to be 2 pipes. Each identified pipe, despite its layout, has to be of constant diameter. But the pipe could contain pumps or valves, and we can just include that in our energy equation as necessary. Now, what do we mean by a junction? Well, a junction is the endpoints of a pipe section, and it could also be a point where we have a specified flow demand. Flow demand could be an inflow or an outflow. So, for example, if I have a straight run of pipe of constant diameter, that could be considered a single pipe, but if I have a demand placed at some point in that pipe, then now this is 2 separate pipes, because any point of a inflow or outflow has to be a junction, and a junction is the endpoint of a pipe. Okay, fixed grade nodes are self-explanatory. It's a reservoir or a tank. It's a body of water of constant energy that is not changed during the analysis. And a primary loop, it is a loop circuit that does not contain any other circuits, and we'll discuss this a little bit more when we set up the equations for this equation. And fundamentally, when we have a network, so we have a network relationship that tells us that the number of pipes is equal to the number of junctions plus the number of primary loops plus the number of fixed grade nodes minus 1. And this equation is important, and it's going to be how we determine sufficient equations to solve for the unknowns. And again, when we're doing the loop equations, the number of pipes is the number of unknowns. Okay, so here's our network relationship. Before we move on, really the quantity number of fixed grade nodes minus 1, that is a number of pseudo loops. In this example, clearly we have 2 fixed grade nodes labeled alpha and bravo, so we have 1 pseudo loop. So let's talk a little bit more about why loops are very important to us. And it is that we're going to be applying conservation of energy around the loop. And if my end point is the same as my start point, then the change in head is going to be equal to 0. So when I march around a loop, for example, say this left triangle, and I do assume a direction for that cycle, I will march around and apply conservation of energy, and then I will set that equal to 0. Now for a pseudo loop, the change in head is known but it's not equal to 0. For example, as we will see, the change in head for the pseudo loop will be fixed grade node alpha minus fixed grade node bravo. And then I'm going to apply conservation of energy from a path going from fixed grade node alpha to bravo, or vice versa, and set it equal to the change, the difference in the fixed grade node. So any loop, be it a primary loop or a pseudo loop, the head is known. If it's a primary loop, a true circuit, then the change in head around that loop is 0. If it's a pseudo loop, the change in head is unlikely to be 0, but it is known because we know the heads in the fixed grade nodes. Okay, so we're going to go through here and identify all the pipes, and it doesn't really matter how you do that, so I'm just going to march around and label them. So pipe 1, 2, 3, 4, 5, 6, 7. So we have 7 unknowns, and apparently writing on the screen my 6's really suck. So 7 unknowns. So my unknowns are Q1, Q2, all the way up to Q7. So those are our unknowns. Okay, so here's our pipe labels. Now let's go through and identify all of our junctions. And again, the way you choose to do it may be different. So I'm going to just march around 1, 2, 3, and 4. And so I have 4 junctions, and I'm going to be applying continuity equation to those junctions. So that gives me 4 equations. I have 7 unknowns. So some way or another, I need to come up with 3 additional equations, and we'll be walking through that. So next, let's go ahead and identify our primary loops. And remember, a primary loop is a loop that does not contain an internal circuit. And so in this network, just by inspection, there are 2 primary loops. And so I'm going to take the triangle on the left and say, identify that as a primary loop. And the triangle on the right is also a primary loop. But what is not a primary loop is if I march all the way around the outside of this circuit. Now that is a circuit, that is a loop, but since it contains internal circuits, it is not a primary circuit. So in terms of the algebra, it does not provide independent equations. So in fact, it's not helpful. And so there are network analysis tools that allow us to do this. You determine the spanning tree and stuff like that, which I'm not going to get into here. But oftentimes, a simple network like this, you can just do it by inspection. So I'm going to be applying conservation of energy around the primary loops. I'm going to be applying continuity to the 4 junctions. So that gives me 6 equations. I have 7 unknowns. And so now I need to identify my pseudo loop, define it. And I'm going from fixed grade node alpha to fixed grade node Bravo. And doesn't really matter which path I go. It should not contain any circuits. And so I'm just going to march along the bottom of this hydraulic network, and my pseudo loop will contain pipe 1, 5, 4, and 7. That gets me from fixed grade node alpha to Bravo. Okay, so I've identified my pseudo loop, my primary circuits. Now let's go ahead and guess a flow direction in each of the pipes. And this is a guess. You could be wrong. Likely might very well be wrong. That's okay when you solve for the analysis. If you get a flow that's that is negative, that just means it's going in the opposite direction that you assumed. So don't spend a lot of time on this. You do need to be consistent once you do that. So clearly I expect flow coming out of the fixed grade node 1 going through pipe 1 in the direction from left to right. And pipe 2 I'm going to assume is flowing into node 2. Pipe 5 I'll assume is flowing into node 4. Coming out of Bravo, I expect the flow going into node 3. And I'm going to assume that the flow through pipe 3 is going towards node 2. And for node 4, I'm going to assume flow for pipe 4 is going towards node 4. And pipe 6, I'm just going to guess the direction that's going from node 2 to 4. So we will be using those guess directions, but don't worry if you got it wrong. Okay, so now we said that we're going to apply continuity to each of the 4 junctions, so let's go ahead and do that. So now let's work with junction number 1. And I'm going to cast these equations so they're always equal to 0. So I got flow coming in through pipe 1. So that's Q1. Coming out of the junction is Q2 and Q5. So that's minus Q2 minus Q5 and set that equation to 0. Now let's do a similar application for node 2. I got flow coming in through pipe 2, so that's Q2. I got flow coming in through pipe 6, so that's going to be plus pipe 6. I've got flow leaving through pipe 3, so that's going to be minus Q3. And I should not forget is that we have an external demand here, which I've labeled small case alpha. And so that is leaving junction 2, so that's minus alpha, and set that equation equal to 0. Now let's do the similar type application to node 3. You see how we're doing this. So I got flow coming in from pipe 3, so that's Q3, plus flow coming in through pipe 7, plus flow coming in through pipe 4, as I guessed it, and I've got, again, an external demand labeled as small case b, so minus b, and set that to equal to 0. One more node, junction 4, got Q5 coming in, minus Q4 leaving, minus Q6 leaving, no external demand, so set that equal to 0. All right, so there's 4 of our 7 equations needed to solve this network. Okay, so now let's apply conservation of energy to each of our primary loops. And big picture, conservation energy is just going to be energy in minus energy loss. Energy in would be a pump, for example. We do not have any pumps in this network, so we're not going to have that term. And so we're really going to have energy loss. And the equation for energy loss is typically Darcy-Weisbach equation, Hazen-Williams equations. There could be others. We're going to simplify that and just say our head loss is equal to some pipe coefficient C times the flow in that pipe squared. So we're not going to be defining what the coefficient C is or anything like that in this video. Clearly you will need to when you actually solve it. But let's go ahead and apply conservation energy to our 2 loops. So our first loop consists of pipe 2, 6, and 5. We have assumed flow directions. So I'm going to start at junction number 1. And I'm going to say, well, I'm going in the direction clockwise as I assumed. And so in the direction of flow, my energy is decreasing due to losses. So I have minus C2 times Q2 squared. And now in pipe 6, I'm going in the opposite direction of the assumed flow. So that's going to be plus C6 times Q6 squared. And then taking me back to junction number 1 in pipe 5, again, I'm going in the opposite direction. So the head loss is a head gain. So I have plus C5 Q5 squared. And that's equal to 0. Again, it's 0 because I started at junction 1, went all the way around the loop, and returned to junction 1. Now let's do the similar type thing for a primary loop, the second primary loop consisting of pipe 3, 4, and 6. So let's say I'm starting at junction number 2. So I have the head loss C3 times Q3 squared because I'm going in the assumed flow direction. So that's a loss. In pipe number 4, I'm going opposite to the assumed flow direction, so that's going to be plus C4 Q4 squared. And then in pipe 6, I'm going in the assumed direction, so that's again going to be a loss, so minus C6 Q6 squared. And again, it's a primary loop, so it's equal to 0 because I started at junction 2, worked my way around, and returned to junction 2. So that gives me 2 more equations added to my 4 equations of continuity for the junctions. So that's 6. I need 1 more. And again, I get that from my pseudo loop shown here in gold. So I'm going to start at fixed grade node alpha and go through pipe 1 in the assumed direction. So that's minus C1 Q1 squared. Through pipe 5 in the assumed direction, so that's minus C5 Q5 squared in the assumed direction of pipe 4. So that's again minus, it's a loss. C4 Q4 squared. And then I'm going in the opposite direction through pipe 7. So that's a gain. So that's plus C7 Q7 squared. And that's equal to the fixed grade node at B, but I'm going to set the entire equation equal to 0, so I'm going to subtract off minus fixed grade node B and set that equation equal to 0. Okay, well, really, that's pretty much it. So let's review the equations. I've got 4 equations by applying continuity to the 4 junctions. I've got 2 conservation of energies applied to the 2 primary loops, and I have conservation of energy applied to the single pseudo loop. Okay, before we move on, even though we're not going to be solving for this because essentially we're done, we should note that all these terms are squared, all the flow terms are squared, and I said that if you guess the wrong direction, that's okay because you'll get a negative number, but the square of a negative number is a positive. So typically when you actually set up the equations, you'll cast the q squared terms in terms of the flow times the absolute value of the flow. That way, if it's negative, you will capture that negative sign, excuse me. One other thing I should point out is that, yeah, we are not solving for the piezometric head at any of the junctions or any location, but that's okay. Once we have the flows, we can just march around. And if I want the head at 1, again, it's the pressure head plus the elevation head. That's going to be equal to the head at fixed grade node alpha, and I subtract from that the head loss through pipe 1, and we can do that for all of our junctions and solve for the hydraulic grade line at every point in the network. So again, now we have these 7 equations. These are the loop equations. So the unknowns are the flows in the pipes. There are various techniques to solve this. In my other videos, I've covered the Hardy-Cross method and the linear method. And in a future video, I think I'm going to use the modified linear method and solve this exact network. So take a look out for that if this interests you. I do hope you found this interesting and useful, and I hope you have a great day. Please like and subscribe, and I'll see you next time.